Hello everyone. In this lecture, we are going to talk about the counters. So counters are one type of sequential circuits. Those are capable to count. So we do understand what is counting. Counting generally starts from a number, and in a sequential way, we keep on increasing that value. So let's say if a counter is starting from, let's say, 0 and then 1, then let's say 2, then dot dot dot, and it is reaching to one particular value, let's say n minus 1. Such kind of counter we can consider as up counting. So such kind of counter we consider as up counter. If a counter starts from a maximum value, let's say n minus 1, and then it decreases that value to n minus 2, and then it reaches like n minus 3, and then dot dot dot, let's say it reaches to 0. Such kind of counting we consider as down counting. Okay, so these two types of general counting we may have. Now let's look at few of the properties of counters. Then we also look the construction of the counter. So counters are sequential circuits. Sequential circuits we have already discussed. That means counters are capable to store the data. So it will be able to manage the previously generated state. Counters are used to provide accurate timing and control signals. So this is the fundamental use of counters. There are two types of counters: asynchronous counters and synchronous counters. So let's look at the difference between the synchronous and asynchronous counters. Synchronous counters, usually counters when we construct, we use multiple flip-flops. So if we want to generate 1-bit counter, there will be one flip-flop only. If we want to generate 2-bit counter, then there will be two flip-flops we have to use. 3-bit counter, 3 flip-flops will be required, and so on. So in synchronous counters, let's say we are having flip-flop, and let's say I'm constructing 2-bit counter. So there's a flip-flop. In counters, generally we use JK or T flip-flop because we need to use the toggling property. So JK is having one criteria: when both the pins J and K will get high value as 1, then it will toggle. This is a state Q and this is a state Q bar, let's say. Now counters or flip-flops, they may have level triggering or edge triggering. So I'm considering here it is negative edge triggered flip-flop. If I consider another flip-flop that is also, let's say, JK, so this is another flip-flop you consider. This is representing J pin, this is K, Q and Q bar. This is also I am considering as negative edge triggered. So there is a clock we are passing here, negative edge triggered. So the symbol represents negative edge triggered. Right? Now based on the connection we establish, the counter will be considered as synchronous or asynchronous. So as the statement says that all of the flip-flops respond to the same clock instance. So if we pass the same clock to all the flip-flops which we are going to use, so in case you connect this clock to this clock, then these two flip-flops will activate or deactivate at the same time synchronously. So the circuit will behave synchronously. But in case if you want to make asynchronous, then we do not connect this, then it is saying the output of one flip-flop derives the clock of another flip-flop. So in that case, what we can do, the output of one flip-flop like this can be passed to as a clock to another flip-flop. So this circuit will behave as asynchronous counter. Okay, after a while we will discuss it in detail. Now this is obvious also, asynchronous counter will be slower than the synchronous counter. So it is faster than the asynchronous counter, and asynchronous counters are slower than the synchronous counter because of this clock and the activation of the flip-flops. Due to design complexity, synchronous counters are rarely being used in IC fabrication, and asynchronous counters are generally being used in IC fabrication. There are two modified form of the counters in case of synchronous counters. So the simplified version of synchronous counter is also known as shift counter, that we will see later. And the modified form of shift counter, there are two, that is ring counter and Johnson counter. So all these counters we will discuss later on. As of now, I hope it is clear to everyone. So let's discuss the 2-bit up counter in the category of asynchronous counting. So because asynchronous counters are primarily we are going to use in IC fabrication, let's discuss the asynchronous counter. Okay, so let's consider there are two JK flip-flops. You can number them also. So let's say if I'm saying this is A and this is B flip-flop. Both these flip-flops are negatively as triggered. This is also negative as triggered flip-flop. We are passing a clock. So let's say we are passing a clock here. Now this clock which we are passing, I am representing here. So let's say this is the clock. This clock has been given here to this flip-flop. So it is connected here, right? Now in counters, we use the toggling property of JK flip-flop. So we know that the JK flip-flop will toggle only in one situation, when J and K both will have value 1. So we pass at both the pins, we pass high value or 1, and here also we want to pass high value or we want to set 1, so that these flip-flops start toggling whenever the clock will become, that transition will happen in the clock according to the triggering. So let's connect these. So we can connect these pins like this. I'm connecting, let's say, this pin with this, so that the same value can be propagated, and this pin we can connect here with this, like this. Okay, now because we are talking about asynchronous counter, the output state of one counter will control the clock of other flip-flop. The output of one flip-flop will control the clock of other flip-flop. So we will pass this output as the clock pulse here. So let's connect this like this. So there is clock is coming. The output is being passed as clock here, and it is connected like this, right? So when we are having this connection, I can give name like this is QA because there is A flip-flop, and this is representing QB. This is B flip-flop. So this will represent QB bar and this is QA bar, right? Now in terms of the clock, let's try to draw the timing diagram for this QA and QB here. So let's draw it. So when we draw it, it will look like, right. So let's draw the QA. So I'm writing here QA. So when QA is coming initially, I assume that QA was 0. So let's say I consider QA was 0 initially. So it is 0. Okay. Now because these flip-flops are negatively edge triggered, we need to highlight the negative edges, because whenever the negative edge will encounter, the flip-flop state will toggle. So negative edges when it is moving from high voltage to low. So this is negative edge, this is negative edge of this pulse, this is also negative edge, low to high, on high to low it is happening, high to low here. This is also negative edge, high to low voltage, this is also negative. These edges, the voltage is changing from low to high, so these will be positive edges, right? So because these two flip-flops I have considered negative edge triggered, they start toggling whenever the negative edge encounters. So if it is 0 initially, it will not toggle, the state will not toggle, it will be 0 only till the negative edge will encounter. Once the negative will encounter, this will be converted to high. Now this is high, and it will be high until the next negative edge will encounter. So this is high till this. Now again this, so this is representing QA, the timing diagram of QA pulse. So here it will be toggling and it will again reach to level 0. Then it will be 0 till the next negative edge, and then again it will become high. Then again it will be high till the next edge, and then it will again toggle and become 0, and then again it will remain 0, and then again it will become high for this edge, and so on. So this will continue like this. Now let's draw the timing diagram for QB. So initially I am assuming QB, initially QB is also 0. So let's assume QB is 0 initially here. Now QB will toggle from 0 to 1 whenever the negative edge will encounter of the clock pulse. But for B flip-flop, the clock is QA. So it will be dependent on QA, and the negative edges in QA are these edges. So this is negative edge, this is negative edge, because the voltage is changing from high level to low level, and the next negative edge will come later. So that means this QB will not toggle here, and it will be 0 till this point. Now it will toggle, so it will become 0 to high here, and it will keep on remain high level till this negative edge encounter, and then again it will toggle and become low, and then it will maintain the low level like this, right? So this is the timing diagram of QB pulse, right? Now how this circuit is behaving as counter, or you can say how this circuit is behaving like up counter. So I'm writing this circuit is actually up counter, behaving like up counter. Initially in the very first pulse, if you look at, this QB and QA. QB we are considering as MSB and QA we are considering as LSB. So this will be treated as MSB and this is LSB. Okay. So if this is MSB and this is LSB, the combination you can represent like this. So let's say here it is QB and it is QA. So the combination when you write in the very first pulse, QA is 0 and QB is also 0. So the very first pulse will give us output as 0 0 because we are considering QA and QB as output of the counter. So let me consider here we are connecting two pins like this. We are getting this QA as output and here we are getting another terminal. So this is QB. These two are giving you the output. This is QA and QB pin. Now the combination of QA QB like this, in the next pulse when it is here, this QA is becoming high. So this is high for this complete second cycle. So this was the very first cycle. I'm saying this is the second cycle, this will be the third cycle, and this will be fourth cycle, this will be fifth cycle of the clock. So in this is 1 and this is 0. QB is 0. So QB is 0 in second cycle and QA is 1 in the second cycle. In third cycle here, QA is 0 and QB is 1. So QB is 1 and QA is 0. In fourth cycle, QA is 1 and QB is also 1. So both are 1. Now in fifth cycle, QA and QB both are 0. So we start getting the same sequence again. So that means after this point in time, we will again repeating the same sequence. So that means this circuit is behaving like up counter. It is starting from 0. So it is starting from 0. 0 1 means 1 in binary. If you convert binary to decimal, it will give you 1. 1 0 means 2 and 1 1 means 3, right? So this is behaving like up counter, or you can say 2-bit up counter, which is asynchronous in nature. So this is sufficient for this lecture. Thank you everyone for connecting. See you in the next class.